Today we're looking at lesson 4.4, and this is all about writing proofs. Today we're looking specifically at proving triangles are congruent, and we're going to look at two postulates, postulate 4.1 and postulate 4.2. Postulate 4.1 is called the side-side-side congruence postulate, and basically it says if three sides of one triangle are congruent to three sides of another triangle, then the triangles are considered congruent to each other. So we're going to do a flow proof, keeping that postulate in mind, and this is telling us that we're given that triangle QRS is isosceles. So if I'm going to label this as isosceles, that would mean these two sides would be the same. QR is congruent to SR, and that basically is what I just put. And then RT bisects QS at point T. So if RT is bisecting QS, that means QS is going to be two equal parts. So I'm also going to label those two parts as congruent. So with that told to us, we now need to conclude that, or prove that triangle QRT is congruent to triangle SRT, and we're going to use a flow proof. Even though, like I said before, it's okay to use a two-column proof, I'm just going to show you what a flow proof might look like. So, a flow proof starts just like any proof, where you have the given statement. So we have triangle QRS is isosceles with QR being congruent to SR, and that is basically put in a box, and given is underneath. So from that, we're going to use that eventually to prove that QRT is congruent to triangle SRT, but we'll hold off on that. Then we have another given, RT bisects QS at point T, and we're going to put that in a box, and that is also a given. So from these two givens, we're going to have arrows pointing out of them in order to eventually get to our proved statement. So from the second statement, the RT bisects QS at point T, like I said before, that the word bisects means split into two equal parts. So if we're going to put, as I labeled, QT congruent to TS, we're going to write that out. And we can use that as a statement, and our reason would be the definition of a segment bisector. And then we're going to also, this goes back to way back when we were talking about the reflexive property, and since RT is in the middle here, in between QRT and TRS, those two triangles, and it's sharing a side, that means we can say that RT is congruent to itself. So we're going to write that down. That actually is going to be kind of in a box by itself, because that doesn't come from either given. So we're going to put that down, and that is the reflexive property. And then so from all of these, from the first given to the definition of a segment bisector to the reflexive property, all of these are going to eventually tell us that we can prove that triangle QRT is congruent to triangle SRT. And the reason why is if we look at our triangles now labeled, this is using the side-side-side congruence postulate. So postulate 4.1 or S you could write as your reasoning. And that is your flow proof. The next example, we're given two triangles and we're given the vertices of them. So our first part to this problem is to graph them both. Usually I would say to graph them on a coordinate plane using graph paper, but I'm going to just graph it right here. So we have 2, 5, 1, 1, and 5, 2. So that would mean let me start by doing this. Each line here is going to be 1 unit. So if I'm going to graph 2, 5, I'm going to go over 2 and up 5, put a point. That's point J. Then I have point K, 1, 1. And point L, 5, 2. And I can draw the lines here. And then my other triangle, negative 3, 0 for N, negative 7, 1 for P, and negative 4, 4 for Q. And that will be my other triangle. So what I need to do now is I need to use my graph to make a conjecture as to whether the triangles are congruent. So thinking about what we just did with the side-side-side congruence postulate, what we can do here on the graph is we could find the distance of all three sides and compare it to each other. And if they are the same distances, then we can conclude that these two triangles are congruent. So that's what we're going to do. We're going to use the points that they gave us to find the distance. So if we go back to the beginning here, the triangle JKL has points 2, 5, 1, 1, and 5, 2. So we're going to basically just go around the triangle here and find the distance of everything. So we're going to find the distance. Let's start with JK. So from JK, that means we're using 2, 5, and 1, 1. Using the distance formula, that's going to be our y's and our x's. So 2 minus 1, 5 minus 1. That gives us 1 squared plus 4 squared, or 1 plus 16. So between JK, that's going to be square root of 17. And then we're going to do that again. So let me write that here. Square root of 17 equals JK. Let me go back. Use the distance formula for the next two. So KL. So that's 1, 1, and 5, 2. So 1 minus 5 and 1 minus 2. That's going to give me negative 4 squared and negative 1 squared, which is still 16 plus 1, or the square root of 17. So KL is also the square root of 17. And then one more. We did JK and KL, now we have JL. So using our points again and the distance formula, JL is 2 minus 5 squared plus 5 minus 2 squared. that gives me 2 minus 5 is negative 3 squared, plus 5 minus 2 is 3 squared. That gives me 9 plus 9, or the square root of 18. And that's going to give me, for JL, the square root of 18. Now we do it with the second triangle. So NPQ. Let's find these three sides. So the square root of, let's say NP, so negative 3 minus negative 7 plus 0 minus 1. That gives us negative 3 plus 7, which is 4 squared, plus 0 minus 1 is negative 1 squared, so 16 plus 1, or the square root of 17. So NP is the square root of 17. So we're on the right track here. Looks like they might be congruent. We'll see. Now we need to keep going. PQ. So negative 7 minus negative 4 squared, plus 1 minus 4 squared. Negative 7 plus 4 is negative 3 squared, and 1 minus 4 is also negative 3 squared. So that gives us 9 plus 9, or the square root of 18. So that is PQ. And the last one would be NQ. And if this is the square root of 17, then they are congruent. So let's see, NQ, negative 3 minus negative 4 squared, plus 0 minus 4 squared. That gives me 1 squared plus negative 4 squared, or 1 plus 16, which is the square root of 17. So NQ is the square root of 17. So if we label this now on our graph, we have JK and NQ being the same. And then we have NP and KL being the same. And QP and JL being the same. And that would tell us that if we are trying to make a conjecture that they are congruent by the side-side-side congruence postulate, we can say that they are congruent. And writing a logical argument using coordinate geometry to support the conjecture, basically what that means is using the distance formula like we already did. That would be our third statement here that we need to talk about. So this would be using the distance formula. That would be called coordinate geometry, because we used our coordinates from our plane to use the distance formula and then support our conjecture that we just made about the triangles being congruent. All right, moving on. One more postulate. This is postulate 4.2. This is called side angle side congruence. So it says if two sides and the included angle, meaning the angle in between the two sides that are congruent, so right here and right here, if all of that is congruent on one triangle and then congruent on the second triangle, then we can say that both triangles are congruent. So keeping that in mind, we have the wings of the hang glider shown appear to be congruent triangles. They appear to be. But if FG is congruent to GH, which they've labeled, FG and GH, and JC bisects FGA, or FGH, angle FGH, that would make these two angles congruent. Okay, we need to think about, okay, how can we prove that the true triangles FGJ and GHJ are congruent. So if we set this up, we could set it up as a two-column proof. Our givens are that FG is congruent to GH, JG bisects angle FGH, and that's our given. And then eventually we're going to prove the two triangles are congruent. So if we start with our given, we then can talk about the word bisects, and if that's going to be this right here, bisecting the angle, I said that FJG, angle FJG, has to be congruent to HGJ. Oh, whoops, I labeled this wrong. It's going to mean this and this angle, sorry, because this is bisecting it. Whoops. These two angles, because this is bisected. FGH, I read that angle wrong. So not FJH, it's FGH. So these two angles are congruent. So FGJ, FJG, it doesn't matter. Or no, it does matter. FGJ is congruent to HGJ. And let me go back and show you, this is what I mean. These two angles are congruent, and that is just the definition of an angle bisector. Just like the last one we did, the proof was the definition of a segment bisector. That's what a bisector does, split into two equal parts. We also used this on the last one, and that is the reflexive property. So if you look, GJ is shared by both triangles, so we can say that it is congruent to itself. So GJ is congruent to GJ. That's the reflexive property. And then if we look at this again, the two triangles are congruent to each other because of postulate 4.2. Because if we look, we have a side, we have an angle, and then we have another side. And then a side, an angle, and another side. So the angle is in the included part of the two sides, so that matches SAS, or the postulate 4.2. And then finally, we have one more two-column proof, and you'll notice that many of these two-column proofs or proofs have been the same, using many of the same statements and reasons. So in this case, we have MN is congruent to PN, which is labeled, excuse me, and LM is congruent to LP, which is labeled. We need to prove that angle LNM is congruent to angle LNP, so we're kind of going to go a little bit backwards here. So first we put our givens, and that would be MN is congruent to PN, and LM is congruent to LP. That's our given. And then by the reflexive property, might as well use that for a third time, LN is congruent to LN. Because in order to say that the angles are congruent, we need to prove that the triangles are congruent first. So that's the reflexive property. And then now we can say that the triangles are congruent, because if you see, you have all three triangle sides congruent to all three triangles. So triangle LNM is congruent to triangle LNP. And that's the side-side-side postulate. But that's not what it's asking us to prove. It's asking us to prove angle LNM is congruent to angle LNP. And since the two triangles are already congruent, we can use this, which we actually used in one of the other lessons, CPCTC, which means congruent parts of congruent triangles are congruent. So since the triangles are congruent, we can say all the parts of the triangles are congruent. So that concludes lesson 4.4 on proving triangles congruent.